course is given by Pierre. And Pierre is a senior researcher at INRIA Mediterranee in Sophia, Antipolis, close to Nice. And he has been involved with organizing the SGP since its beginning. For example, he organized the second SGP in 2004 in Nice. And one of his lines of research is concerned with surface approximation and mesh simplification. And today he will give a course on this. So, stage is yours.
Hi everyone, welcome back from lunch. I hope you are ready and not too sleepy with this light. So, simplification and approximation. So, I prepared a talk where, because it's a grad school, I don't know what's your profile. So, the beginning of it will be the standard simplification topic. I will discuss the main components of such algorithms, metrics, and so on. And then I will move to approximation that involves more like optimization algorithms, again related to also metrics. And then I will do more toward, I will evolve toward more like a research topic or recent work on providing guarantees, algorithms that come with guarantees. On topology, on geometry, and I would like to spend also some time on the remaining challenges. So I thought it could be appropriate for some of you, if you are finishing your PhD, some of these topics, at least I think each of them could be a topic for a postdoc or something like that. So first, the material. Some of the slides are taken from this book. I hope you know it. Mario Watch is in the room. You will not recognize him. Okay? But he is in the room. And this book, when we gave a course at the time on polygon mesh processing, one chapter is on mesh simplification. So there is some material from Mario, and also some material that I did with some co-authors, David Cohen-Steiner, Mathieu Desbrun from Caltech, Florent Lapart from INRIA, and Manish Mandak, who is now a postdoc in Aachen. So what's the motivation? Motivation, simply, is to generate multi-resolution hierarchies with lots of details, either for efficient geometry processing or for efficient level of detail rendering. So there are many, many other motivations for generating approximations. The overall goal, put it simply here, is to optimize for a trade-off between mesh complexity and the so-called distortion or error metric. And of course, there are many ways to express the complexity, and also very many ways to define an error metric. Okay, so today, I will especially go through this because of freedom. And of course, the way to generate the meshes, there are many, many ways to do it. You can do that through mesh decimation. In the first part of the course, you can do that by refinement. I will not talk about this. You can do that by meshing at a specific, starting with a lattice, mesh lattice, and then simplify that. You can do that by clustering, by partitioning, and so on. Many, many ways to proceed. And what I think is so interesting is not just these, is also what other properties you may want to look after, in addition to optimizing for this trade-off, and I will discuss that throughout this tutorial. So the point statement is very simple. You are given a mesh to find the vertices and faces, let's say, and you want to find another mesh such that either the number of vertices is smaller and you want to minimize this error metric, or you specify a so-called error tolerance, maximum error tolerance, and then you want to minimize the cardinality, like the mesh complexity. Okay, you can see this on the two sides. There are just two instances of the same problem. It amounts to say that on that curve, that trade-off curve, either you fix one, is the axis of this curve, or the other coordinate. This is hard problem. This is probably NP hard problem, already even for the approximation of the terrain using a piecewise linear function of a triangulation. This is probably NP hard. So here, typically in the literature, there are many variants that look for suboptimal solutions. You can also add additional fairness criteria where you may want to control other things like the distortion over the normals, the shape of the triangles, the appearance attributes. I won't spend much time on that. I will start right away with the simplification. I think if some of you raise their hand saying, we all know this part, like her, it could go a little bit faster on simplification. So, we start with the vertex clustering basic, yes?
Sorry, which norm are you using?
The error metric?
Yes.
I will discuss that. There are many possible error metrics. For the moment, I don't fit any, okay? For the moment, I will just...
But whichever you take, it's NP hard.
I don't, okay, from the paper from IGS'16?
Because you claim that
yes, this, no, I think in their proof, they fix a certain norm. And I think it's probably like this Hausdorff norm, and I think the optimality means the global optimum, like the lower number of vertices. So vertex clustering, first approach, very simple. The idea here is to proceed by clustering the data. So imagine you embed the mesh into a uniform 3 degree, and then you simply map all the vertices to the cluster cells. Very simple. I go quick on this part, just remind some of their use. And you can use either the article approach, job to down. You can, instead of using a regular grid, you can use a binary space partition. You have degrees of freedom on how to cut the space, and so on. You can do that either in an axis-aligned manner, the way I showed you initially, or the hierarchical manner, and so on. The basic principle is that the 1 degree of freedom is which representative do we choose once we perform the clustering. And quick overview of that is if you select, let's say, the average of the vertex position, you simply do some like the analog of the low-pass filter, just average the vertex locations. You can also choose like this analog of the median vertex position here. It's like performing a subsampling of the data. You select a subset of the vertices. Or another very popular metric is called this error quadrant, and I will go back to that later. That is much more effective at preserving, as you can see, the sharp creases in the features. So we go back to this metric, and I'm here. So this particular metric is has been introduced a long time ago, but it's still, interestingly enough, it's still hard to beat. It's very impressive to see that the idea is extremely simple and extremely efficient also to implement, and it's hard to beat. It has also some drawbacks that we'll discuss. Let's say you have a plane. This is, let's say I consider a plane with its normal equation. Okay? It's a normal form, namely where this ABC are the coefficients of the normal. And when this vector is a unit vector, you have this defines, you can define the equation of the plane this way, where D is the sine distance to the origin, and ABC are the coefficient of the normal. And then if you are given a point, you can express the square distance to the plane in this form. And then here, let's say you have a triangle mesh. Assume you are given a set of planes. Of course, they will be typically derived from the mesh initially. And then once you express this square distance to the plane, you have a so-called quadratic error metric that will be used to drive to define the vertex locations. So if you want to typically to minimize the sum of distances to the vertex planes, then you simply have to solve a linear system to find the points that is locally optimal. And then to generate here the mesh, we just simply compute the clusters, and we will be connecting an edge. If there was an edge between these vertices here, you can have topology changes if differentials pass through one cell like that, it can become non-manifold, while if it was manifold before, we will prove that we preserve the topology here. Okay, so I go quick on the vertex decimation, on the vertex clustering. Now I move to the iterative decimation. And then we spend more time on the metrics. So in the iterative decimation, that's the most classical approach in literature. You have hundreds of variants based on iterative decimation. So here, in my against the abuse, you have to repeat the following operation. You select an area, a region on the mesh. You apply a decimation operator until no further reduction possible. So typically for each region, we need two things. We need to evaluate the quality after decimation. So we have somehow to simulate this decimation of the region. Then we have to also, evaluating the quality means, of course, simulating also the optimal vertex location after the clustering or after the decimation. And then we have to enqueue to insert into typically a modifiable quality both the region and the quality after simplification. So what the algorithm looks like that, we repeat the best mesh region, apply a decimation operator and a data queue. That's the pseudocode. So now if you look at the degrees of freedom of this type of algorithms, you have decimation operators. And first we need to define what is the region. What are the degrees of freedom for the triangulation? And then you have typically classification like operators that are topology changing versus preserving, and subsampling versus filtering. So one operator, classical vertex removal, select the vertex to be eliminated from the mesh. You select all triangles sharing this vertex, remove the selected triangles, create a hole, and then you fill the holes with the triangles. And of course, you see this vertex insertion, which is the inverse operator. So basically, what we have here are combinatorial degrees of freedom. Okay, because there are several ways to triangulate this polygon. So there are will be some discrete optimization. Why? You see, I removed really one vertex, didn't touch the other ones. That means this is a subsampling algorithm. And typically, there are algorithms that perform some kind of discrete optimization. So another operator is the very classical, the edge collapse operator that merges two adjacent triangles, removes three edges and one vertex, and then you have to define a new vertex position. That's a continuous degree of freedom. You have to define this vertex location in space, and that can be seen as a filtering. Then you have special cases that is called half-edge collapse. It's when this time it's a special instance of the previous one when we collapse just the edge onto either the source or the target vertex of an edge. That's this time. There are basically, once you define the operator, there are no more degrees of freedom. Okay, you just populate your Candy queue with twice as many operators as the number of edges. But this time you can do a more efficient algorithm in some cases, and that's subsampling. So the edge collapse, if you look at it, once you apply the edge collapse, it proceeds like that. You see that in some cases you have to be careful. You have to add some other, what we call fairness criteria, but let's say if you want to preserve some other properties, some metrics such as, let's say, the normal orientation and so on, you may need to be careful here to prevent this type of operations to proceed or to add that to your optimization. Now, in terms of error metric, okay, so I go quickly, but now I want to spend more time on these metric issues. Here, first idea here was a long time ago, shorter, it's the local distance to the mesh that was approximated as follows. Simply was on the neighborhood, they were computing the average plane, kind of the fitting plane locally, and measuring the distance to that plane. That means that there was basically no comparison to the original geometry. We were always referring to the mesh itself incrementally, so you could really drift and not really be able to bound it at all. And this is one approximation. This is an approximate metric. Another metric that we defined in 99, it's kind of a long time ago, was the volume. The volume of what? You could argue that this is not always well defined. Let's assume for the moment I have two closed surfaces. And I am able to define a volume embedded between two watertight and surfaces that have a valid embedding, say. Each of them is decision free and so on. So in that case, you can construct an algorithm, either a mesh optimization algorithm or even a simplification, in which this time we were able to minimize the volume between the two meshes using an algorithm based on gradient descent, where we simply minimize the volume between the two surfaces. And these operators, I'll skip some of the details, but in these operators, all we needed in this optimization algorithm, all we needed was this relative orientation for each point sampled on one of the meshes. The relative orientation being, is that point location on the mesh, am I above the other surface or below? If you are able to query that thing for any point sampled on one of the meshes, then you can derive a gradient descent algorithm that minimizes the volume between the two surfaces. Okay? Well, intuitively, if you think about this volume-based metric, think of that you are consider an infinitesimal move of a vertex of one mesh that you want to relocate. In that case, you can see that if you consider a local parameterization of the surface, let's say a little square du dv of your local parameterization, you see that if you relocate that vertex in whatever normal direction, you can express the elementary sign volume of your surface, and from that sign volume elementary, you can construct progressively a kind of finite element approach to minimize the volume. So once you apply this volume minimization, you see that this mesh is deformed to minimize the volume with another mesh, actually sharp features and corners. And that metric, compared to other metrics such as L2, is shown to better preserve the sharp features. So then there was an approach by Lindstrom-Turk called here. That also was using a volume-based metric, but this time they made the following observation. This time it's a memory-less algorithm. Memory-less in the sense that there is no reference, there is no query to the input mesh, the way I was doing through my relative orientation thing. Here, they observe that when you collapse an edge of the mesh, when you collapse an edge, the triangles, they sweep, when they are located in space, these triangles, they sweep the volume. Right? And then you can, and this volume will be signed, and then you can relocate the vertex such that you minimize the change of volume include, and you can even cancel it, change of volume performed by this edge relocation, edge collapse operator. So this is again kind of, it's volume preserving but memoryless. Okay, you just kind of iterate the value mesh. You can have a little bit of drift, but this algorithm performs extremely well. And this is what's implemented in the CDAR library, by the way. So now we talked about this. This is basically was this local volume preserving approach. Here was a local error metric. This quadratic error metric was also something that's locally expressed. And now there was here the goal of this simplification envelopes work was to obtain a global error metric and to be able to bound the error. So what I propose here is to compute so-called offset surfaces on the input mesh. And they added the following constraint that they are not self-intersecting. So here, imagine we offset the input mesh in the two directions in order to generate so-called simplification envelopes. And then they guarantee that the simplification will stay within the bound. I will come back to this method later. So now there is something. So this is in fact a one-sided Hausdorff distance. Okay? This is an asymmetric geometric because you bound only in one direction. And to my knowledge, I have very few papers that deal with this two-sided Hausdorff. There is in particular one paper I just mentioned quickly using a two-sided organization here. This two-sided Hausdorff distance, well, this time we want to bound the distance between two shapes. So in general, note that the distance, the Hausdorff distance between A and B is different from B to A in general. It's often very compute intensive to compute. So this is, for instance, the distance from A to B, the maximum distance from A to B here over here, and the distance from B to A. In general, they are different. And the main added value to use a symmetric geometric that will be typically preserving better the boundaries of the mesh. In some cases, also the features, although it's not really probably, let's say, better feature preserving than other metrics. But in general, it's more powerful to be able to prove things, like to bound the deviation in the two directions, but it's usually much more compute intensive. So this looks like that for the one-sided Hausdorff distance that's often used for data sets that are densely sampled, typically initially. In that case, it's reasonable to say that if we are sampling densely the original vertices with current surfaces, it will be often sufficient for some class of applications. And this will give you here the closest point on the simplified mesh that is used for simplification. So now, if you look at this, again, this error matrix, here, what I depict here, I come back to the quadratic error matrix this time. So here, suppose you have this point, P1, this vertex P1, with its own quadratic error metric attached to it. Just compared to the, remember this quadratic metric that I presented before, this ellipse is supposed to depict the ISO level of the error. Okay? So that means that assume around the vertex, that vertex will be flat, this ellipse will be degenerated, completely flat. Okay, completely flat. That means that when you move along the line, parallel, let's say, to the two edges adjacent, if it will be flat, the error will be zero. Okay. So now the trick with the quadratic error metric is to add some memory to the system by saying that when we collapse the edge P1, P2, we are going to keep a memory of the stencil around P1, the stencil around P2, through simply summing up the two quadratic error metrics. See the trick? So the trick here is to say, at each step, every time we collapse an edge, we keep a memory of what was the mesh before through accumulation of quadrics. So there was a work a long time ago, I remember in a workshop, that proved that in some specific cases, this accumulation can be wrong. Okay? This is one of the drawbacks of this metric. And I remember that I don't give you all the details here, but it was shown that if the mesh, the input mesh, is completely, let's say, very, very noisy, this quadratic error metric, after you decimate many, many times, or many, many vertices in the mesh, this quadratic will not represent at the end, after accumulation, a faithful descent to the original mesh. Okay? But in practice, in the application, this is extremely effective. And then here, typically, when you can invert this quadrant here, then you will find the optimal point location that will minimize the sum of squares to these planes that were themselves the results of an accumulation. So yeah, this is maybe the most popular approach for mesh simplification. You have an invert, and I will do that. So there is no really a bound on the true error. Okay? It's at all step an approximation. Plus, when you select the plane here, the plane is an infinite proxy, right? That means that virtually you kind of prolongate the surface at infinity. Thing to accumulate. So that means that you will have anyway, it's an approximation, and we're not bound to true error. Yeah, this is how it is depicted. You see that on some parts like the Pierre's, you will have very cigar-shaped ellipses that show you that you should indeed, that there the error really does not increase much if you stay along that here. And they look like a plate on nearly planar areas. And if you have a corner, if you have a sharp corner, like on this table, it looks like a tiny ball state. So now, quickly about fairness criteria. So the first thing to rate in the decimation operators. Typically, you have a priority queue, and you need, therefore, to define what's the priority. Plus, you need to define if you allow or not an operator, or if you discard some of the operators in the priority queue. One is, of course, the approximation error, so you can sort the priority queue by that. Then you can imagine that you can have many other criteria. I won't spend much time on that, but typically you can add that you want to preserve the shape of the triangles. But this is slightly more touching the topic of remeshing, because you want to control the shape of the triangles, which may, of course, contradict the goal of minimizing the complexity of the mesh. Diagonal angles may want to preserve the normals, and this also touches another topic. I will go back to that later, to the idea of metrics that preserve not just the geometry, but tends to preserve also a device to preserve the normals. And the balance, and so on, and even the color differences or any type of appearance attributes such as here colors, or it could be texture coordinates, and so on. So there have been hundreds of work, typically, adding good to have properties, other criteria in the array. About topology changes, there has been also a variant that allows to merge vertices across so-called non-edges. So for vertices that are distant, because sometimes if you have many, let's say, connected components, you'll be stuck in the decimation. And if you want to go further, you have to merge also these vertices, and this is called the generalized edge collapse operator, typically in the literature, and or here vertex contraction or vertex separation. In that case, you need to augment your data structure with a spatial neighborhood information. It can also generate non-manifold meshes, like that. So if we compare, vertex clustering very often is extremely fast, but it's often difficult to have some control. You have degrees of freedom, like I mentioned, the way you proceed with clustering. We allow topology changes. You can have some global error bound, but you are often far from the optimum. If you look at the iterative decimation approaches with quadric metrics, you have usually very good trade-off between mesh quality and speed. You can have also explicit control of the mesh topology through the atomic operator. You can, if you have two manifolds initially, you can easily add operators that can use operators that preserve it. Now, if you look at the extensions, there has been a number of extensions in several directions. I mentioned only 3 of them here. Some that are pretty old stuff, like out of core. Out of core is for data set that do not fit into main memory. So there has been a variance by again Gallen, also Cobalt and Heisenberg, who deal with data sets in a streaming manner. They are able to receive a mesh in a streaming manner and simplify gigantic meshes this way, using a nice first reordering of the data. But not of the time, the algorithm loads the mesh into main memory. It's always a tiny fraction of the mesh that is stored in main memory. U-dependent, this is a variant where you can either simplify with where the metric is biased to better preserve, let's say, things such as silhouette or the distance to the visualization and so on. But this can be also done in a more clever manner where you can first recompute, record a sequence of decimation in the form of an acyclic graph of operators. And then later on, during visualization, you can query the progressive data structure that will display the mesh in the view. Something much more recent that we did recently is very simple idea. This was presented at the last Eurographics. It's in Computer Graphics Forum paper. It's called, I did that with David Salinas and Florent Lafarge. It's called Structure-Aware Mesh Decimations. Here the trick is extremely simple. Let's say you are given a city. So we have done that for a specific field of urban modeling. Suppose I have a city like that. And now you want to better preserve what we call the structures here, namely the sharp resist and so on, sharp features of that city. One solution, very simple, you first detect planar parts in your city. You see here I've detected using a ransack type, ransack-like algorithm. I've detected some planes. If you are using the standard down-headed approach, you will be performing well. But if you are simply augmenting the set of planes that come from the mesh, right, that come from the triangles, the way I explained before, you augment the set of planes by the set of planes that come from a planar detection step, plus some other structure-preserving rules, adding just that to the standard down-headed algorithm, then you will be better preserving the structure. Okay? You can, this algorithm, this type of algorithm, it is possible to leave the door open to just better preserve the structure that has been detected through prior analysis of the input mesh data. Okay? And this algorithm has been also already been integrated into an industrial product for modeling of large-scale cities. Okay, this concludes the first part, which is about standard mesh simplification. Are there any questions about that? Yes?
That last paper that you showed, was the intuition that the traditional aggregation of the quadrics gets confused when you add together the noisy planes, or what?
Yeah, typically it's not enough, exactly. So it will be typically not enough to preserve what we call the structure. Will be, in fact, I said that we also preserve structural rules. Suppose you detect using ransack some planes. You can also, once you have detected these planes, you can construct a graph. Let's say an adjacency graph, okay? That you can infer and that you could even simplify on the way. But then suppose I say that I want to preserve that structure. Let's say I don't want two planes that are not adjacent, I don't want them to become adjacent, because this would pinch a big bit. And we are adding this so-called structure preserving rule simply to the algorithm using an adjacency graph. And that's all. Otherwise, we just augment the quadricular metrics by these planes. We don't do, in fact, this is something we are currently also investigating. We want to investigate better an assessment of how much let's say, badly conditioned are the initial quadricular metrics. This is something we are currently working on, but this is more research topic. We would like to, the way we do it right now, that we traverse all the scales, and then we perform an analysis on kind of the conditioning of these matrices to better weight between the importance of the structural planes versus the initial products. Okay. So I will be back to the metric issues because I've touched the metric several times. I mentioned Hausdorff, volumes, symmetric also. I mentioned the normal slightly. And you see I've added already a little bit of structure. No more questions? So I can go with the approximation. So for the approximation, I will not tell you about the whole state of the art over here. I will this time make a focus on this approach. But then I will use this approach to discuss more the metric issues that we are casting on. So here, in this approximation, this approach is called variational shape approximation. It was published at SIGGRAPH a long time ago. The rationale here is very different. You take an input mesh. This is an input surface triangle mesh, and this time I want to generate a partitioning of that mesh such that something that is close to piecewise linear approximation on this partition is a good approximation of the input mesh. The rationale is in fact to cast the surface approximation problem as a so-called variational K-partitioning problem. I mentioned to you before this idea of these results by Agarwal and Zuri. It's about this piecewise linear approximation or interpolation of a function of a terrain, of an elevation wave, I suppose. In that case, the problem is stated this way. We could say that, we could restate the problem. We could say, we want to partition the mesh with elements that are simpler, in piecewise linear. And again, either with a given fixed number of partitions we want to minimize the error, or vice versa. So here, you see that somehow in the problem statement now I have a problem, the issue of partitioning. Okay? So suppose I want to first have a look at the simpler instance of that problem. Suppose I want to partition a 2D domain. Okay? Much simpler problem. With regions that are here, Voronoi cells. And my generators will be points. You see these black points over here, they are the generators of my domain. It's a much simpler instance of that problem. Here, I want, let's say, suppose I want to find a partition that minimizes the following energy. This energy sums up over the Voronoi cells, where the K are the indices of the regions, the Voronoi regions. This is a density function, rho of x. Suppose this is a density function I'm given. And this is what? This is an integral over each Voronoi region of the square distance from any point in that cell, x, to the generator, which is this black point. So basically what we want to minimize here is the sum of square distances to the generator. Suppose this is a simpler instance of that problem. I want to find a partition that minimizes that energy. That energy is not related to an approximation at all, but it's more like a variance minimization. See, right? So now there is an algorithm to minimize this energy. It's called the Lloyd Iteration, and this algorithm consists of doing the following. You compute the Voronoi partition. By the way, for a fixed set of points, it is the Voronoi partition that minimizes that energy. Because the Voronoi partition is based on the Euclidean distance. So that's the one that we minimize for fixed points that energy. And that's even the global minimum. So now, for a fixed partition, suppose I fix the partition, what is going to be the best generator, the xj, in that equation? The point that minimizes the sum of square distances in a cell, that's the centroid, the center of mass of one cell. Okay. What we are going to do simply is called an expectation maximization approach, in which we are going to alternate between these two minimization algorithms, but we are going to minimize the same energy at each step. Okay, there are 2 degrees of freedom. In that energy, in that equation, the first degree of freedom are which are the regions, and the other one is which are the generator of energy. And we are simply going to hammer on that energy with 2 hammers. One is the Voronoi partition, the other one is vertex relocation. And a necessary condition would be that for the optimality is that it is a central Voronoi distillation. So if you look at that algorithm quickly, if you look at this algorithm, it looks like that. This is a Voronoi diagram. Okay, I remind you. I don't remind you what's a Voronoi diagram. And I depict here the centroids. And the Lloyd iteration does the following: move to center of mass until you have the central Voronoi distillation. Okay, and if you add in generators like that, you will have that your algorithm will iterate between partitioning and vertex relocation. And you see there is something else interesting going on over here, is that if you insert more generators over here, you are going to compress this cell over there. That means that you are minimizing a sum of squares, and therefore the optimal solution will try to equalize the energy in each Voronoi step. Okay? So now the concept is as follows. Suppose that my generators, this point, black point over here, suppose they are not points anymore. Suppose they become planes. Okay? My generators are planes, I call them proxies, because there will be a local surrogate for geometry. I can do that on surfaces. Suppose I do that on a curve. My generators will be planes. And then I will partition the surface, where this time instead of a Voronoi diagram, it will be the part of the geometry that are the closest from the plane. And then vertex relocation will be what? Will be relocating a plane to the best fitting plane to its region. Okay? So it will be a kind of principal component analysis like approach when the error metric will be the L2 error. Okay? So the way it works, I can show you that I think on the surface. Suppose I take a simple surface for now. Suppose I have this like that. So now suppose I generate 6 random planes initially. Okay, I can even depict these planes using this. And now I can do the same. You see that every time I'm adding a new plane, and I can add this, every time I'm adding a new plane, this error will be again equidistributed. Okay? If I restart randomly, they will again be optimal. And you can again observe the same type of process. Suppose I do that, is that okay, you see that I will have this equidistribution of the energy even on this simple. Okay, and if I'm adding a proxy, one more, it will equidistribute the error. And if I remove a proxy, it will always equidistribute until just finding the best fitting plane. It's principal component analysis for that surface. Okay? We call that variational partitioning because the error now is this integral formulation, and we really perform some relaxation and some optimization algorithms. Okay, so now once we have done that, the concept is very simple. See, distortion will be the integrated error between the region and the proxy. The total distortion will be the sum of the proxy distortion. And the best K approximation will be for us the minimum distortion. Okay? It's kind of approximate algorithm. So the result is as follows. We have the initial mesh plus the partition after optimization, and we have the proxies after engineering. Now it comes to once you have a partition, it's not a trivial matter to generate a mesh. How do you do that? Now we have performed here a so-called discrete partition. So this is the algorithm. It's in fact an analog of the K-means clustering algorithm, not nothing else. We alternate clustering by closest proximity, and we find new generators. So here, now, the issue is about which metric do we choose? If we choose the standard L2 error metric, the sum of square distances from each point in a triangle of the input mesh to the plane, I don't do the other way around because the planes are infinite, okay? So I measure the distance only from the input mesh to the planes. If you look at that error, this integral L2, fortunately, if you choose the L2 error, the local optimum, namely the base free plane, exists in closed form formula. It's a closed form formula. Okay? Although it's an integral formulation, you can derive a closed form from that. Basically, all you need is to compute the covariance matrix of the set of triangles, and there is it. So now, for L2, what we prove is that asymptotically is the aspect ratio of the regions, namely of each region in the partition. The aspect ratio will be shaped with an aspect ratio of square root of kp1 over kp2, which are the principal curvatures. So this matches the theory of optimal approximation with elements, with piecewise linear elements. But if you look into the details, with the L2 error metric, in the elliptic case, let's say for the convex parts, where the two principal curvature directions have the same sign, it's fine, you have a unique optimal from the aspect ratio point of view. But on hyperbolic regions that look like a saddle, there is not a unique minimum. You have a one parallel family of optimal configurations. Plus, there is another issue, is that it's not because you converge in the L2 sense that the normal will converge. If you think of this celebrated Schwartz Chinese lantern, think of a Chinese lantern. Okay, you know that? Favorite Chinese lantern. You can give me a number. You can give me an arbitrary number larger than the area of a cylinder. It has to be larger. Okay? Give me any number larger than the area of a cylinder. I can construct a mesh where all the vertices, a triangle mesh, where all the vertices are on that cylinder and whose area matches that number. To be arbitrarily large. In other words, the normals could diverge completely, although all the vertices are on the mesh. So that motivated us to devise or to use another error metric, which would be simply the normal deviation. So we tried that. It's very easy. You have again a closed form formula, even simpler. Why? Because of the triangle, the normal is constant. Piecewise constant, the normal on the triangle mesh. So in that case, we could say, we call that L2-1, L2, because it's the L2 error over the normals. It's the integral of the square differences over the normals. And this time, it's interesting, we proved that asymptotically, we are going to generate regions that have aspect ratio kp1 over kp2. The square root is gone. This time, hyperbolic regions are perfectly fine. And this will be used to capture the normals. So when we tried this algorithm, using the two different error metrics, we saw that on L2, we have indeed, you see the square root of kp1 over kp2 over there. And you see that for L2-1, the aspect ratio is larger, the square root is gone, and visually, at least, even numerically, we better approximate the normals. So this tends also to be better feature preserving. So now, one slightly trickier this time, that instead of taking a mesh, making a decimation, this time we have a partition. How do we go back to a mesh? And to tell the truth, this is not completely solved yet, because although we are more than 10 years later, but I will tell you what we proposed at that time. We proposed to do the following. We have a discrete partition here, where three regions meet. You see, it's a discrete partition. Okay? We have one label that says this guy is closer from the plane yellow, and so on. And for the vertices where three regions or plus meet inside the corner, 2 or plus in the back. all. Then around these vertices, we generate what we call wedges. wedges are angular sectors like that with this color, okay, with the name ID. Let's say this is one ID, another one, and then what we do, it's a kind of constrained de triangulation but discrete on the mesh. We have a two-pass flooding algorithm using, can be seen as a multi-source Dijkstra shortest path. The first pass, we flood only the region boundaries. We tackle these wedges over here. We flood first from here only on the boundaries. And where these floods, these two fronts meet, we are going to add an edge between this guy and this guy from that guy. Then we flood the interior to mimic a kind of discrete parabolic diagram, where this time we flood the interior, and you see now I'm flooding the same ID of these wedges. Therefore, all I need to do is to gather the triangles where three wedges float from, and then I know that this guy was disconnecting this guy, and this guy. Okay? So that means that this triangle will correspond to this large triangle. Yeah, I think the best would be for me to show you a quick demo of that. Okay. Suppose over here, if I start with one proxy, I will run the optimization algorithm, one plane, two planes, and so on. I do that manually just to show you how it behaves. Here. You see that there's always this equidistribution going on, especially on the curves part. So I can have the model, I can even show you that in the form of ellipses, and I can add elements like that. You see that every time I add a proxy on a curved region, the equidistribution occurs. Okay. And then when I've done that, I can extract the mesh this way. I can hide that, hide the mesh. See, that's the triangle mesh. That mesh was constructed this way. We hide this guy, and then we show the wedges. Sorry, I don't remember all the shortcuts. You see, wedges. That means that this guy will connect this guy. Okay, and once we have done that, we can hide this, show again the model. We have a way to beautify the mesh, again, by generating basically convex polygons where possible. That's a way to improve the mesh and generate physical approximation. So again, in terms of metric, L2 versus L2-1. You see this one is much more anisotropic. There is some curvature here. Doesn't look like, but there is some curvature. So that's an example of the standard running. It's 200 proxies. And you see anisotropy is captured well here. So the anisotropy is just the result of the metric minimization. We could also have used another approach that we first estimate the curvature in the mesh and then design a mesh that matches this metric. That is much more difficult to tune because this curvature estimate usually requires a scale factor. That's on the real scale model and after optimization. Okay, so now, what time is it? Still have time. Now I want to discuss with you some guarantees. Let's say this is an overview of different approaches where one is very greedy, the other one was more integral formulation where we minimize the error. What about the guarantees? For some applications you need some guarantees. Think of metrology, also for urban modeling sometimes they want to have guarantees, and sometimes even worse than that, they say we have no measurement. We have measurement data. No measurement, I don't want to invent anything. No measurement, no data. I want a bounded error. What are the guarantees you would like to get? That's a much more, let's say, computational geometry point of view on this problem. What you would like to have, I mentioned that already, is a one-sided Hausdorff. This was already addressed in the literature by several people, and including Mario. And also, two-sided Hausdorff, much more difficult problem. But now you may want also to guarantee other things, like the topology. So then you have several levels of guarantee you could have. You could have something that is intersection, because for some applications it's good to have, or really a strong requirement. You want that the simplified mesh is guaranteed to not self-intersect. Think of 3D printing. You want some 3D printing, you don't want any self-intersection. Something stronger is homeomorphism, that you capture the right topology. Something even stronger is isotopy. Also, there will be some, this time, it's not just being homeomorphic, but being isotopic to a shape, meaning that this time you have that not only you have homeomorphism, but all intermediate deformations from one surface to the other are also have a valid value. So if you look at that literature, instead of having 300 papers or so, it's much smaller number. It's not really fully exhaustive. I think there are probably 10 more papers than that. But let's say I mentioned the main ones: self-Partition envelopes, global error, tolerance volume, distance field, permission grid. Everybody calls it the way he likes. Tolerance volume, so bounded error. Is even this work, Hausdorff envelope. So this guy is mixing Hausdorff and the envelope with the error. If you look at the literature, so here, the contribution of this work was to observe that it's super expensive to compute the Hausdorff distance, and one way to accelerate it is to have clever data structure, GPU-based, and so on, and linear approximation to scientists has been. I hope this makes discussion good. Yeah. Here, Cohen and Al. By the way, Cohen was a paper from '96. I tell you, for those who want to compare, he still has the code, and it compiles. And we had to compare in our paper from SIGGRAPH last year. He sent me the code, he said good luck. And he was right, because this is extremely hard to beat. So I warn you. So it's not because it's a code from '96. This is really hard to beat. So this is the way they construct the simplification envelopes. Almost impossible to beat, except that when you specify a large tolerance volume, because they force the offset, the way they construct the offset is constructive, they cannot offset more than a certain value that is conservative. That means that basically, if you specify in their case a large tolerance volume, they are stuck by generating a smaller tolerance than the value you want. So I would say it's almost a perfect solution, but for large tolerance values. And you have, in these approaches, they don't change the intersection field property. It's something else. Well, sometimes they do. In some approaches, they do also the ones that bound, but it's hardly the case that you have all the guarantees altogether, topology and variability and bounded error. There is, to my knowledge, a single paper that addresses only the problem of intersection free. It's called intersection free simplifications. This time, they run the standard Gallon-Hilbert edge collapse-based approach, but they prevent the creation of intersections. This is very nice, but this tends to end prematurely, because you just prevent, so you stop decimating. Plus, if the input mesh intersect, what do? You are stuck, you need to repair. Okay? So, this now I will discuss another work that's very recent, SIGGRAPH last year, done again with the usual suspects, Cohen Steiner, and Manish Mandal, PhD student, former PhD student at INRIA. Here, it's different. We call that isotopic approximation within a tolerance volume. And I will discuss that work now. Unfortunately, I don't have a live demo on my laptop for this work, but it's pretty impressive to see this algorithm working, except that it does not really scale. It's slow. So, I remind you the motivation. This is really this time we consider the two guarantees altogether. I want to have, this time also, by the way, I changed the problem statement. I say this time that I am given just the tolerance volume. I don't care what is inside. Okay? Doesn't mean that the problem is easier for the user, because as a user you have to define a proper tolerance volume. But let's say this way will be robust to anything that was in the tolerance. And then we want to generate as output a surface triangle mesh that is within the tolerance volume, strictly within. Homotopic equivalent to the tolerance volume. What does it mean? It means I could take the tolerance volume, shrink it, such that deform it to the input to the triangle mesh, such that at all steps I can define variable. So think of the difference between a torus, double torus that is knotted versus not knotted. One would not deform it without crossing its shaft. That means we want topological guarantees, motivation for simulation, machining, printing, and so on. And we want something else, which is the minimum number of vertices. And this, I'm back to the initial problem statement. This is hard, right? This is very hard. So for the moment, we revised our animation. We say we want a low vertex count. I will go back to that later. So the approach, we started from a completely different viewpoint this time in this work. We didn't want to simplify the mesh. Why? Because it could be the case that the input already intersects. So I don't know how to guarantee things like that. If the input should be repaired. So I much prefer to consider another result that from Shazar and Polissener. It was a paper from 2004. It was a theoretical results that stated the following. It's called a condition for isotopic approximation. So I'm not telling you all the details, okay? I will go a little bit faster. It tells the following thing. If S prime is included in a topological thickening M of S, that means what? Suppose I'm given S and S prime, two surfaces, such that one is included in a topological thickening of the other one. And S prime separates the side of M. S prime is connected and its genus does not exceed the genus of S. Then the two are isotopic. Very good. So here we started from this theorem and we said, okay, let's make an algorithm. It's called a constructive approach that will match these conditions. Remember, this is like a sandwich thing. I want that the surface separates the two sides of the topological embedding, the topological thickening. So we have to build a kind of a sandwich where one surface, our surface, will separate the two sides of the thickening. So our approach is the following. We take this time the tolerance volume, and the trick is to not deal with the surface at this point. I don't have a surface, I have a volume, that's all I have. What we do, suppose our life is simple to start with. I have only two boundaries on my tolerance volume. I call that d omega 1, d omega 2. We first compute a point sample on the boundary of the tolerance volume, and we put the label, let's say, +1 on this first point set, -1 on the other one. And I skip some of the details, but the sampling should be dense enough so that the set of bolts of radio sigma cover d omega. Otherwise, I will prove it. Okay? Remember, mathematics, same on computational geometry. You have a proof, but very often you have a list of requirements. And the goal is to lower this list of requirements as much as you want, but this one we could not do more. Then we construct a triangulation on what? On a subset of S. S, remind you, this is our point sample. Okay? So it works like that. We construct a Rolling triangulation on a subset of the sample. So here this is by drawing kind of confusing. You could have other yellow points much more dense than that. Okay? But now I will construct a piecewise linear interpolation function on the triangulation. It's going to be a volumetric function. And I will insert some samples of S until the zero set of that interpolated function classifies well the +1 and the -1, such that the +1 are on the right side, -1 on the positive side, negative side, and vice versa. Okay? I go between. And what do? We say the following. We say that, let's say this is the sample S. We say that the sample S is well classified if that value, which is f is the piecewise linear function, while capital F is the label I assigned. And we say that when the sample is well classified, it's good, otherwise it's bad. You see that these guys are well classified, and these red ones are badly classified. Okay? It's a matter of sign. And then what we do, once we have that, we have a zero set, which will be a surface this time. What we are going to do, we are going to simplify using standard edge collapse this volumetric mesh while preserving the classification of this. And then there will be another step that I will go through. So the algorithm is greedy. I remind you that initialization, one function value per connected component. Things get more complicated when you have more than 2 boundaries. You may have n boundaries. In that case, it's slightly more complicated. You need to enumerate all possible combinations within a triangle that has level +1, maybe -1, and so on. All possible permutations, and all the samples should be well classified modulo all classification, all permutations. I will accelerate it a bit. So the intuition behind this algorithm is as follows. We first refine using the Delaunay triangulation until we capture well the topology. The idea is we discover the topology first. And then we are going to perform a fine-to-coarse simplification, not Delaunay anymore, in order to discover the geometry, the anisotropy in the data. Okay? I will just, instead of telling you all the details, I'll just go through the algorithm to illustrate. One sample here, in simple case. The triangulation of a loose B box of that guy. Okay, we compute the loose B box from 2 points very far away like that, 4 points. That gives us some samples that are badly classified. And then we insert one at a time the samples that are badly classified. Okay. And while we have bad points, we insert these points in the triangulation. You see, so you go through a step where it's crazy. The zero set crosses everything. And at the end, worst case, you have to insert all the samples. And then they are trivially well classified. Okay? Yes?
How do you actually make the choice which of the samples
yeah, the trivial choice we could argue could be the one that is the worstly classified, but there is something better to do than that. You can reuse the kind of idea of polygrammetry there to perform a local piecewise linear approximation in order to locally reorder within each triangle. The details are in the paper. I skipped some of the details. Yes?
One problem is quite obviously because some of the earlier points might be just on the line between inserted points, so that a new inserted point makes an old inserted point really redundant, and so you can skip it actually.
Yes.
So this is one of the problems probably also with this.
Yes.
Because it's greedy.
Yes, that can happen. That can happen that you have another. But we will simplify this triangulation. So it's not over. Right now, it's the coarse-to-fine approach to discover the topology. So now the topology is right. Now, what we do is we are going to simplify the triangulation. We can simplify it using half-edge collapse operator and so on. It's a volumetric triangulation this time. But that classifies, that preserves the classification. And then, so we have that. And then it's not over. We perform what we call a mutual decimation. We insert the zero set, the black curve, we insert that into the triangulation. Namely now, we have a mutual decimation, and this is going to be our transition from a volume to a surface. Now the surface mesh is the black mesh inside the volume mesh. And now we simplify this guy while preserving the classification. Okay, so it looks like that. Mutual decimation and simplification. So on a non-trivial shape, previous one was trivial, this is less trivial, this is curvy and linear over here. You see the classification goes, okay, good classification. Okay, see the way it goes, like that. So now the trick is that this is going to be very expensive. Why? So first, I forgot to mention that in the mutual decimation, when we perform it, we set the zero set in the triangulation. And then there is another trick, is that you can approximate the tolerance volume itself by a bunch of different people. Okay, we call that the simplicial tolerance. And we can use that to accelerate the computations. So now, it's complicated because suppose I have this edge to collapse of the zero set, do gamma samples, and so on. We need to decide, we need to preserve two things. First, the topology. This is so-called a link condition. I'm supposed to go really fast on this one. It's just to preserve the topology of the mesh. It remains as three-man. It's called the link condition by Desbrunner and Day. And then something much more complicated to compute. We need to preserve the valid embedding. What does it mean? It means that after collapsing an edge, but think this time it's a volumetric mesh. After collapsing an edge, I need to make sure that I don't create any set intersection. And this is called the kernel condition. You see this kernel? This is a kernel of the union of the Turing of these two vertices. Okay, you see this polygon? The kernel is a locus of points that see all the boundary of the polygon. From this point, I can visualize all the boundary of my polygon. If the kernel is not empty, I can safely collapse an edge with the vertex in that kernel. Okay? And this, I skip some of the detail, this is computed using linear programming to know if there is a kernel or not. And then I can relocate safely within that kernel to a location that will be, by the way, a quadric geometric C. This guy has an empty kernel, for instance. This guy, there is no way you can collapse this edge. So now the trick is that for an edge like that, to collapse it for this edge over there, the kernel can be tiny like that. So it's really different from this quadric geometry plus the check of absence of intersection. Now I have a tool for optimization. I know if there exists a location in space that will guarantee. Okay? This is a non-empty kernel, this is an empty kernel. So now the trick is that plus in addition to the valid kernel, we need another test, this is the kernel. Plus we need to preserve the classification of the samples. So they remain well classified. That means that kernel should be intersected with another region that is possibly very complicated that will preserve the classification. Okay? I don't tell you how we do that, all the details are in the paper, but you see that if you want to have some guarantees in terms of topology, you need to pay for it. There is some square quadric geometry going on over here, is that to choose among all these points in the blue area, search for the sum of square distances between the target vertex and the Turing planes, the supporting planes of the triangles of the zero set that are at the distance 2 in the graph. And this guy, follow me again, will give you the best point of this. We add some option to also preserve the normals, as keep some of the details. Some of the results, you see the first step is a refinement step. Delaunay refinement, and here what I did is only the zero set. The zero set is made up of quads and triangles, right? Slice tetrahedron, and have quads and triangles. Then we simplify the boundary of the tolerance volume. Then we simplify, there has been some mutual tessellation going on. We simplify the zero set, and then we simplify all possible edges we can, including edges that connect the boundary and so on. It's a bit expensive, but at least we discovered first the geometry and then the anisotropy with it. So now the question is, how do we perform? So now we have an algorithm that is kind of counterintuitive, because if we want a small tolerance volume, our algorithm will be very costly. Why? For a standard mesh simplification algorithm, if you simplify a little bit, it will be faster. If we want a large tolerance, then typically, large tolerance, you will have a smaller number of vertices over here. And you see that the refinement is extremely fast, and all the decimation, all this kernel test is very costly, okay, because this is the time. The good thing with this approach is that not only we have the guarantee, tolerance, and error bound, but also we can repair the data. Why? Because we don't care about what was in the tolerance volume. There is not even the fidelity test to the data. There is not even a term that says I want to be faithful to the input. I don't care. Just do whatever I want in the tolerance volume, whatever I can. So that means that even for data set like that, we will generate a mesh that is like. So now we haven't solved the main issue of robustness. Why? Because now we delegate to the user the design of the tolerance volume. And that turns out to be, again, another problem. Okay. So how do we compare? I told you it's very hard to beat the simplification envelopes. So we are slightly better over here. The other methods are worse. Okay. And they create self-intersections, dots. This is when we measure one-sided Hausdorff distance in one direction. We are also better in the other direction. That's good. But where we are superior, like I said before, is that tolerance simplification envelopes, they cannot simplify something like that. When you give a large tolerance volume, they will stop. This is all they can do, because they cannot create a big offset surface. So they will stop here, while we can really generate something. So I'm done with, let's say, an overview. I hope I was not too specific, but at least I showed you a few approaches. One focusing on guarantees, the last one. Others on global, let's say, variational formulation. Others are greedy, and so on. Now I want to discuss, to take the remaining time to discuss some of the remaining challenges, okay, what I consider is really hard problem. So the first one is, of course, on the error metric. The question, we play a little bit with L2, L21, Hausdorff, one-sided, and so on. What is hard, what is also very interesting, is what about a Sobolev norm? Something really much more general. Let's say I want to preserve geometry, and the normals, and the curvature. What does it mean? I think for those who saw the talk of this morning, I hope you thought about this curvature estimate or something like that. I hope that's the case. Suppose I want to have a mesh that is simplified, but on which the curvature estimate is faithful. I would like to have a generic approach, okay, in which I could plug a sort of generic norm. This is a hard problem. Other thing that is very hard is a two-sided error. Two-sided computationally is extremely hard, but I don't like the symmetrized error metric, because you have papers in the literature, they say, oh, it's a symmetric Hausdorff, or it's a symmetric error metric, but in fact, by definition, the metric is not metric, they just symmetrize. Okay. You have other metrics, typically optimal mass transport metrics, and the champion of this metric, at least from the computational point of view, are Quentin Rigaud, Gabriel Pierre, Justin Solomon also. There is a metric that is called optimal transport. This is extremely interesting. It's called Wasserstein distance, because this metric is by definition symmetry. You can very well say that you transport some mass from one surface to the other, and that metric is extremely powerful. Another remaining challenge is the robustness to wide range of defects. Suppose I have an input mesh really defect laden with a lot of holes, overlaps, cracks, and so on. How do we define a metric that is really robust? We only scratch the surface of that problem, not in the context of mesh approximation, but rather in the context of surface construction. We did that with Julie and the usual suspects here, using optimal mass transport. But this is really, that would be a perfect topic if one of you is willing to, I don't know, collaborate with us with this topic. How do we perform a mesh simplification where it's just a Wasserstein distance metric? Because this is amazingly robust to noise and imperfect data, outliers, and so on. Another thing is structure aware. I mentioned to you before an approach in which we have incorporated some of the structure, right, based on planar detection, but it's still an open problem to devise a metric that would also incorporate the notion of structure. Because structures can be potentially very rich, can be adjacency, can be even structure, geometric regularities, coplanarity, orthogonality, things that I want to preserve. It could be hierarchical decomposition that I want to preserve as well. You know, the structure is polymorphic, very rich, it could be combinatorial, it could be also continuous, and so on. And the question is, how do we devise a metric that would incorporate this notion of structure? That's perfect topic, I think, for now, for us to work on. Because if you think of an urban scene, you see these big cities, you cannot regulate the structure in these cities. It seems like for industrial applications, they come back to us, now the industrial people, they say, can you generate levels of details that are meaningful? And then we are left with this word meaningful. And then when we ask them, what do you mean by meaningful? They don't really know. But there is some notion of structure. A very hard challenge that we, by the way, are currently working on, but only brainstorming. Some of you have an idea. I think that it's a nice idea for perhaps one day to cut paper. It's, can we devise an algorithm that is progressive? And you could say, it's not progressive in the sense progressive meshes, okay? It's something else. It's progressive in the sense that, think of this tolerance volume paper. I would like an algorithm where I can guarantee that every CPU cycle you give me, I will use it to progress toward the global optimum. Okay, that means that, suppose this is a global optimum. Let's say for the tolerance volume, the minimum number of vertices. Okay? This is NP-hard. This is extremely difficult. I agree. But suppose I want to guarantee that if you give me more time, I don't want to get stuck. I want to make some progress. Even if every step is more and more expensive, I don't want to get stuck. Why? Because some industrial applications, they tell me that they have a cloud, they have 5,000 cores on their cluster. It's not a problem to simplify for a night. They want to specify a night of computation. And they want to make sure that when they come in the morning, they can stop the algorithm when they want to. Not the other way around. As you say, we stop because we don't know what to do. That's a difficult problem. Right now, the current solution we have involves simulated annealing and so on. It's really the best we can do for the moment. It has some simulated annealing going on. And if, of course, the operators become non-local. It's not just an edge collapse. It's edge collapse that may involve the relocation of all the other vertices within the tolerance volume. Intuitively, what we do, we'll tell you a bit what we do, we select a guilty edge, we pick an edge, random, we call it guilty, and then we cannot collapse it, okay? Otherwise, we would have done that easily before. We cannot collapse it. We don't collapse it, we just make it shorter. A little shorter. This is easier. And we make it shorter and shorter and shorter until we can collapse it. If we cannot collapse it, we roll back everything and we choose another GTH. Okay? That's right now the best results are based on this type of ideas. It's just to say if you cannot collapse, you can make it shorter. That's all. What we are missing is the proof. Huh? Okay? We are missing the proof. Something else, open problem as well, is why triangles? It's a bad idea. Why should we use triangles all the time? Triangles are bad, in fact. They are not even generally the best type of polygon of element we should use. This is a diagram. I'm sorry there is no detail for it, but suppose I have a curvature estimate on my surface. Did you see a curvature estimate yesterday? Or suppose I'm able to estimate on the surface the curvature of Kp mean and Kp max, the two principal curvature directions. Remember, they are signed. Okay, so I can plot the following diagram. This is Kp mean, Kp max. That means what? When one of the curvature is 0, here, the surface is parabolic. It's a piece of a cylinder, right? Piece of a cylinder, concave. Piece of a cylinder, convex. This is hyperbolic. This is a saddle, right? Convex in one direction, concave in the other one. If you read the paper by Basilio, it's called Are bilinear triangles better than linear triangles? The answer is yes, of course, they are better. And especially better if the surface is hyperbolic. Not only they are better, they are superior convergence. The error decreases in cubic fashion, not quadratic fashion. Plus, you should not use a quad, normal quad way shape. You should use a rhombus. The best is the rhombus. You take a rhombus with two vertices on top of the saddle, two in the middle, two at the bottom, and the saddle in the middle is superior convergence. Guess what? These edges line up with a zero curvature direction. So it's not surprising, right? And they are asymptotic direction. Curvature 0. Of course, they are linear edges. That means what? The best mesh you can build is made up of rhombus on saddles, on quads, on near parabolic areas, on near spherical paths. You should never use something else like hexagons with a proper interpolance, something hexagonal dominant. And in between ellipses, here should be anisotropic meshes. And somehow the triangles, where are the triangles? They are good. Except that if I give you a cone, think of a cone. It's good to have triangles for a cone, right? That means the surface is close parabolic there, but the zero curvature is turning. In fact, it's a quad that has generated into a triangle. So this suggests us that maybe we should also explore a topic like that. Something else, a challenge that has been already explored a bit by people, other people like Schiffer, Mitra, is beyond abstraction, beyond simplification, beyond approximation. It's called abstraction. Let's say you want Eiffel Tower, but you want an abstraction of it. You don't care of being faithful. You want something else. You want a handful of primitives that approximate well the essence and the structure of this model. And the abstraction should involve something like filtering. Filtering means you should forget something at some point. That means the metric itself should be able to say, at this point, I forget completely this part of the data. Instead of saying, I am faithful all the time. Okay? So it's very, very complicated problem. Plus, something beyond approximation, I call that meaningful loss, level of details. This is what I told you before. This is a paper we did, was presented, it was a talk paper presented at SIGGRAPH in 2013 by Yannick Verdier, Lafargue, Florent Lafargue, and myself. on levels of details of pure benzene. This time, it's not only the structure that's important, it's also the semantic. Because you have pure benzenes, this is a tiny excerpt of the pure benzenes. You can have trees, you have facades, roofs, and so on. And meaningful levels of detail for some industrial applications are so-called CTGML formalism. They say this is log 0. This is the layout on the ground. This is log 1. Those are shoe boxes. Just shoe boxes, flat roof. If it's flat roof, you better know what is roof. That's a semantic thing. This is log 2. You start having the roofs and some icons, detailed icons instead of cylinders for the trees. And here you have the facades and the superstructure, namely the chimneys and so on. This, right, our understanding of this problem is that it's hard to forget the semantic. Okay, so how do we devise error metric that take into account the structure, the semantic? By the way, last word, we are hiring. Just got accepted another ERC project. It's called a proof of concept. It's an innovation project. It's called Titanium. It's really to perform some technology transfer and research on also robust geometry processing. So Pierre postdoc or result engineer. If you are finishing your PhD, you would like to contact me. And we have also an ongoing proposal for a project with a very big industrial company from the Silicon Valley, where the topic is on advanced geometry compression. And here, this is a project that is being submitted, but for which we have good chances of success. So it's really about abstraction and compression. Thank you very much.